Welcome back to the deep dive. Okay, so we hear all the time about these absolutely massive AI models, trillions of parameters doing incredible things like writing code, generating text. But there's this weird paradox in machine learning right now. Scale, it turns out, doesn't always mean reliable reasoning. Like you give one of these huge large language models a task that seems simple on the surface, maybe a Sudoku puzzle or a tricky maze, or these geometric puzzles called ARC-AGI, and they just fall flat. Sometimes literally 0% accuracy. It's kind of shocking. So our mission today is to really dig into the source material and uncover this pretty surprising story of how a tiny network is actually succeeding here. It's not just getting by, it's really excelling using elegance instead of just raw power. We're going to trace the path from the, let's say, complicated hierarchical reasoning model, HRM, to this much simpler, much more effective tiny recursive model, or TRM.
Yeah, that struggle you mentioned with the big LLMs, it really comes down to how they're built. They try to solve these complex Q&A problems by generating the answer piece by piece, token by token. It's called autoregressive generation. And the thing is, this method is super expensive computationally, and it's just incredibly fragile. They might use techniques like chain of thought or throw huge amounts of compute at it during testing, but if even one single token in that whole long reasoning chain is wrong, the entire answer can just be invalidated. Poof. That's why, even years after benchmarks like ARC-AGI came out, these AI giants still haven't really cracked reliable, human-like accuracy on them.
And that brings us to the real kicker here, the shock factor, right? TRM gets way better results, better generalization with just one tiny network.
Exactly. I mean, look at the numbers. The best TRM model we're talking about, only 7 million parameters. Yeah. 7. Now, compare that to HRM, the predecessor, which had 27 million, or, the hundreds of billions, maybe trillions in things like DeepSeek R1, which, by the way, still scores 0% on the really tough Sudoku Extreme benchmark.
Yeah.
So, yeah, 7 million parameters getting it right. That's not just a little better.
Right.
It's a totally different way of thinking. It really shows that how you compute can matter way more than just how much compute you throw at a problem. Quality over quantity.
Okay, let's dive into that predecessor then. The Hierarchical Reasoning Model, HRM. What was the idea behind it initially, and why did it end up being so, well, complex?
Well, HRM came from this sort of theoretical place inspired by ideas about how the brain might process things hierarchically at different speeds, different frequencies. And it did have some early success. It relied on two main new ideas. First, this recursive hierarchical reasoning. That meant using two separate networks, $5 running fast, $5 running slower, looping over and over to kind of refine the answer. And the second piece was deep supervision. Basically reusing the internal states, these latent features they call cell-level and cell-level across many, many internal correction steps, maybe up to 16 steps.
Okay.
And that's clever, right? Because it acts like residual connections, letting the network keep tweaking its internal answer. It gives this small model a huge effective depth, maybe like 384 layers deep effectively.
Wow.
Without actually needing the memory of a genuinely massive network. It's like this continuous error correction loop.
That sounds powerful, definitely. But complex ideas often have, hidden issues. HRM leaned on some specific theoretical shortcuts to make training feasible, didn't it? Something about the implicit function theorem, IFT.
That's exactly where the trouble started. See, HRM had to run the model forward like 6 times in one pass, back propagating gradients through all of that.
Yep.
Super computationally expensive. So they looked for a shortcut. They brought in the IFT and use this one-step gradient approximation. The theory says basically you can approximate the overall gradient by only backpropping through the last couple of steps if. And this is the big if.
If what?
If the recurrent process actually settles down, if it converges to a stable fixed point, the IFT was supposed to be their ticket to faster training.
Okay, wait. So they built this efficiency trick based on an assumption that later analysis showed probably wasn't even happening.
Pretty much. Yeah, that's the paradox. The model was just running forward. It wasn't actively trying to find or guarantee convergence. And later digging showed that those internal features, ANCOA way, they were quite unlikely to actually be hitting that required fixed point when using the approximation. So yeah, they built this elegant theoretical structure, but the foundation was, well, a bit like quicksand. The main way they saved time relied on something that wasn't really holding up theoretically.
So if the IFT shortcut was shaky, what about their other attempt at efficiency, this adaptive computational time ACT thing? Did that have hidden costs too?
ACT was another attempt to save compute. The idea was, instead of always running the full 16 supervision steps, maybe the model could learn when to stop early for simpler problems. So they used Q-learning, a reinforcement learning technique to train a little decider head. And it worked. It did reduce the average number of supervision steps needed per training exam.
There's always a but.
But implementing that key learning part meant they had to run an extra calculation through this separate head, and it actually forced an entire additional forward pass through the main network during every single training update.
Oh, wow.
So while it cut down steps per sample, it basically doubled the compute cost for each training step overall. It kind of just traded one cost for another, not really the efficiency win they hoped for.
Okay, so HRM was complex, theoretically maybe flawed, practically expensive. Now let's shift to TRM, the Tiny Recursive Model. It uses just one small network, simplifies everything, and gets better results. How on earth did they pull that off?
Right, so the first big move with TRM was just bold. They tackled that shaky IFT theory head on. They basically said, forget the shortcut.
Just get rid of it.
Yep. They decided the instability wasn't worth it. Instead, they committed to doing the full back propagation, but cleverly. What they do is run the full recursive process, say $2 times. For the first $T times, they run it without calculating gradients. This is purely to let the model refine its internal answer and reasoning. Then, only on the very last, the teeth pass through the loop, they turn the gradients on, and back propagate through that entire final recursion.
Ah, okay, so they still get the benefit of the multiple refinement steps, but only pay the gradient cost once at the end.
Exactly. They traded that unstable theoretical shortcut for just doing the math properly, albeit a bit more computation on that final step.
And the result, just from making that one change, ditching the IFT approximation.
It was huge, like night and day. On that Sudoku Extreme benchmark, accuracy jumped from around 56.5% right up to 87.4%, just from embracing the full back propagation. Stability and simplicity really paid off immediately.
Wow. Okay, so TRM also ditched the kind of complex brain-inspired labels for the internal states, right?
Yeah.
Simplified the interpretation.
Correct. They dropped the whole hierarchical Siltballerson thing. Instead, they gave the two latent features much simpler, more functional descriptions based on what they actually do in the loop. So night, which was kind of like Suloller before, is now just the current embedded solution. It's what the model thinks the answer is at that moment in the loop. And VLE-Zoo, which was like C-Loller, is the latent reasoning feature. Think of it like the model's internal scratch pad, its chain of thought, the steps it's taking.
And you need both.
Turns out, yes, it's crucial. If you don't have dealer, the model basically forgets what answer it was working towards from one loop to the next. But if you don't have Zielera's, it forgets the reasoning, the path it took to get there.
Makes sense.
They actually tested alternatives, like using just one feature or trying different multi-scale setups again. But performance always dropped. This two-feature structure, current answer, plus the reasoning path seems to be the sweet spot for this kind of recursive problem solving.
Okay, and the third big change is maybe the most surprising. The size reduction. HRM had two networks. TRM uses just one. It handles both the reasoning update for $7 and the solution update for $1. That cuts the parameter count roughly in half, right? And yet, accuracy went up again, from about 82% to that 87.4% on Sudoku.
Exactly. It's counterintuitive, isn't it? Simplify the architecture, fewer parameters, better results.
And even wilder, they found that making the network really shallow, just 2 layers deep, gave the best generalization. Adding more layers actually made it worse because it started overfitting.
Yeah, that two-layer finding is fascinating. It really suggests that the recursion itself is doing the heavy lifting for generalization here. The loop lets the model iterate and refine, effectively getting deeper over time without needing a physically deep network.
So it avoids the overfitting you'd normally get trying to train a deep network on, say, only 1,000 examples.
Precisely. The recursion acts as this powerful regularizer, almost. It allows the model to learn complex functions from sparse data by repeatedly correcting itself. It's depth through time, not depth through layers.
Okay, let's look at the bottom line then, the performance. How does this tiny 2-layer TRM actually compare against HRM and those giant LLMs on the really hard tasks?
The results are pretty stark. Let's take Sudoku Extreme again. The TRM MLP version, with just 5 million parameters, hits 87.4% accuracy.
Okay.
HRM, the predecessor, with 27 million parameters, only 55.0%. And the big guys, DUC-GAR1, Claude 3.7, still 0.0% on that specific benchmark. Complete failure.
Wow.
Same story on Maze Hard. The attention-based TRM gets 85.3%. HRM was at 74.5%. LLM 0 again. And maybe most impressively on the newer ARC-AGI2 benchmark, these are really tough geometric reasoning puzzles designed to test generalization TRM with only 7 million parameters.
Yeah.
Get 7.8% test accuracy. Now that might sound low, but compare it to Google's Gemini 2.5 Pro, a state-of-the-art massive model. Gemini only managed 4.9%.
So the tiny model significantly outperforms the giant one on this generalization task.
By a good margin, yeah. Using vastly less compute and far fewer parameters, it's a strong signal about generalization.
So let's bring it back to the listener. Why should you care that a 7 million parameter model can solve a maze or a Sudoku puzzle really well?
Because this points towards a future where high-level reasoning doesn't require building these city-sized AI models that cost fortunes to train and run. It shows a path to getting really robust abstract reasoning capabilities from small, efficient models you could potentially run locally, models trained on specialized, maybe even small data sets. Think about getting that Sudoku result with only 1,000 training examples.
Right.
This is like a blueprint for making powerful AI reasoning much more accessible, affordable, and deployable in the real world. It's about efficiency and reliability.
And you mentioned TRM, MLP, and TRM at. The architecture choice still matters depending on the task, right? It wasn't one size fits all.
Absolutely. Good point. The simpler attention-free MLP version was the winner for tasks with a fixed small input size, like the 9x9 Sudoku grid. It's very efficient for that. But for tasks with much larger inputs, like the 30x30 grids in Maze Hard or ARC-AGI, you needed the self-attention mechanism in PRMAT. Attention is just better at handling that larger context, figuring out what parts of the big input grid are important.
So the architecture still needs to fit the problem space.
Definitely. The model needs the right tools for the job.
Okay, so wrapping this up, it feels like a really clear story about the power of simplification. TRM basically took a complex, theoretically heavy model, stripped it down, ended up with a straightforward, just two-layer network, but kept that core idea of a recursive loop with deep supervision.
Right. They got rid of the dependence on the shaky IFT. They eliminated that expensive extra forward pass for ACT, slashed the parameter count, and the result.
Yeah.
It crushed the performance benchmarks, especially compared to the giant LLMs, showing incredible efficiency and much better generalization on these specific reasoning tasks. It really flips the script on scale versus reliability.
So TRM definitely simplified and boosted deep recursion. But maybe the final thought, the thing for you to really chew on, is why. Why does this deep recursion, this iterative looping refinement, seem to work so much better on these tasks than just building a traditionally bigger, deeper feed-forward network?
Yeah, that's the million-dollar question, isn't it? Part of it might be robustness, especially with limited data. A standard deep network might just memorize the few examples it sees and fail to generalize classic overfitting. But the recursive structure forces the model to refine its process step by step, correcting errors along the way within a single example. Each loop is like another chance to get it right, potentially making it much better at generalizing from scarce data.
So it's the iterative error correction itself that's key?
It seems like it plays a huge role. That ability to iteratively refine, to essentially practice solving the problem internally multiple times, might be the secret sauce here. It bypasses some of the usual penalties of network complexity when data is scarce. There's definitely something profound about that iterative process that we're still unpacking. It's something worth thinking about for the future of AI reasoning.